funding provided by the National Science Foundation.
My name's Sean Farrington, and I'm with University of Delaware Chemical Engineering program. And today I'm going to talk to you about my favorite material, slime. So why do I like slime so much? Well, it's because it's fun, obviously. You can play with it all day long. But more importantly, what I like about slime is that you couldn't tell me if this is a liquid or a solid. Really, because it's a trick question. It's neither. Well, or both. I don't know. But this is what makes slime so interesting and complex. I make this slime with a mixture of borax, which is laundry detergent, water, and white glue, craft glue, stuff you normally have. You can mix it in all different combinations to have different types of slime, some more solid than others. And so this begs the question, how can I decide to have some slime and figure out the proper recipe for that? This is a very scientific question, and it's central to the NRT MIDAS program, where we have 3 ways of doing this. We can use experiment, theory and simulation, which are at the molecular level, and statistics, which we can infer meaning from the experiments and the simulation. So today I'm joined by an expert in theory and simulation, Kronenberger, and he's going to help me explain those bits. But we hope that you enjoy our scientific demonstration of our favorite material, slime.
I'm going to go set up my computer now, so I'm going to leave Sean to do the experiments, and I'll see you guys in a bit.
So our first step to answering our question about how to predict a recipe for the right slime that we want is with experiments. Okay, and our first experiments start out visually. We're going to take some slime, it's like this orange one, and we can kind of bounce it on the table like this, and you see it jumps around nicely. But we take the green one, and we bounce it on the table, and it just flops. Okay, and you can see the difference even more clearly when I roll it into a ball and set it out on the table. Clearly, the green slime is what I like to call more slimy. It flattens out like a pancake a lot faster than the orange slime. Okay? And let's do that again, but now with our blue and yellow slimes. Okay? We roll them into a ball and set it out onto the table. I can't really tell a difference. They look very similar to me, so we need better experiments. And this is where we come to our 2 beakers over here. We have a yellow and a blue, the same weight in both containers, and I have them set at the exact same height. Okay, and then what we do is we flip them over and we watch. Now the slime that reaches the table first is what I would call the slimier of the 2 slimes. And we clearly have a head runner coming in the yellow slime where it eventually reaches the table first. So I would call that a slimier slime because it took less time to fall out of the beaker. There's a scientific term for this which we would call the relaxation time. It's a characteristic of our material that really tells us, how slimy it is, how much time it takes for it to relax. A lower relaxation time means a more slimy material. Okay, and how do we actually measure this? Well, this is where I can take you over to the machine that we use, and I'll show you exactly what we do to measure a relaxation time. So here we have this machine, where we can squeeze together a piece of slime between 2 parallel plates. And we move the slime back and forth and measure the amount of force that takes. And from this, we can actually measure a relaxation time to tell us how slimy our material is. So I actually did the calculations, and you may remember our slime that won, the yellow slime, this was 4 seconds. And the slime that lost, the blue slime, that was 5 seconds. And how about one that's entirely different? The harder slime, 10 seconds. So from this, we can see that with a lower relaxation time, we have a slimier material. So again, we go back to our question, how am I supposed to pick a recipe to make a slime that I want? Well, what do you want me to do? Sit in the lab and make infinitely many combinations of borax, water, and glue and measure them on the rayon all day long? No. While I would love to do that, it's just not practical. This is why we have Stephen to tell us how slimy our material is based on the recipe using the interaction of our slime molecules.
Now, Sean's experiments are pretty cheap, but sometimes we do experiments that are really expensive, and we want to have some idea of what we should expect from those experiments before we go in, so that we don't waste our time or money. Sometimes we also want to know what happens at the molecular level in our system, and so for that we can turn to simulations. Now, to do a simulation, you need to have some idea of the molecular structure of your material. In this case, our slime is made up of these long molecules called polymers that look like this. There are some spots along the length of the polymer that can stick to the borax, which affects how the polymers move, ultimately changing the sliminess of our slime. You can do simulations where every individual atom is represented, but those can take a long time. And so a lot of the times we group atoms together strategically to make the simulation faster. And so each of these beads represents a group of atoms rather than a single atom. We can try to recreate Sean's results with my simulations using a bunch of these chains and these borax molecules. Now, the chain doesn't like to stay like this throughout the simulation, and so it'll tend to scrunch up something like this. So when you put a bunch of these in our simulation box, it'll look like this. This type of simulation that I'm doing is called molecular dynamics, and we can look at the structure at any given time, but it also lets us look at how the molecules move over time. So this is one of the main benefits of molecular dynamics simulations compared to other simulation types, because it allows you to study the properties of your material that depend on time, like our sliminess. Now, for example, we put a bunch of these polymers and borax molecules together. We can measure how each polymer moves and use that information to calculate the relaxation time from the simulation. When we add different amounts of borax in our simulation, we can see a similar trend that Sean saw in his experiments. Often, it's difficult to get an exact match to experimental measurements, but we can get an agreement in trends and a better understanding of what's happening at the molecular level. To get an accurate match, we need a more accurate model for our simulation, but this tends to come at the cost of the simulation taking a lot longer. There are many resources available online to play with simple molecular dynamic simulations, but this is one of my favorites. You can change the number of atoms, the temperature, you can bond atoms together, and even more. Here, I'm starting off with a solid where all the atoms are stuck together and they don't move very much, and then increasing the temperature until it becomes a liquid where the atoms can start to slide past one another, to a gas where the atoms can move freely throughout the box. Similar to experiments though, simulations can take a long time, and so we want to be able to get the most value out of the fewest number of experiments and simulations. So now we're going to bring Sean back, and we're going to talk a little bit about how we can do this using statistics.
To incorporate our final component of the NRT MIDAS program, we have data science. And this is where we can infer some information in between the experiments and the simulations that we did.
So this is our data from our experiments, and we're going to go ahead and plot this on our amount of borax versus relaxation time plot.
We could plot it and it might look something like this. And these are our data points. And what we do to make a prediction is just draw a line through our data. And now we can use this line to maybe, if we want a relaxation time here, then we go to our line and we can measure exactly what amount of borax we need. And this is how we use statistics. We can draw maybe some other lines here which tell us how confident we are in those predictions. And then that gives us some range of values that we have to predict our recipe that we need to get this relaxation time. But this is a simple system. There's only one value and one output.
In lots of the chemical systems that we use, there are plenty of components in there. you might be interested in many other aspects of the properties of the system other than just the relaxation time. And so for those types of systems, we can also use a lot more complex data science algorithms in order to do a similar analysis as this, but just to predict multiple properties and use multiple inputs as well.
So our final takeaway from this video is that the three methods that we showed you today, experiments, theory simulation, and statistics, are what we really use in scientific studies to predict material properties. And so this is shown in many products that you may use, like shampoo, food, blood, and polymer or plastics. And so we hope that you learned a little bit about how these are done and how they're core to the NRT MIDAS program. Thanks for watching.
Funding provided by the National Science Foundation.